Chapter 3, Exercise 35. Show that for any r in X, we have the equivalence class of X modulo R is equal to the image of R under the set X. Okay, so I think we should go ahead and clarify what this new symbol means. Right, and this is called the equivalence class of X modulo R. If you've taken abstract algebra before, you might have some intuition as to what this is. But if not, we'll define it very clearly in just a second. Okay, so this is going to be the set. These square brackets, subscript r, is equal to the set of y such that x r y. The book uses t, but I like y a little better. It just fits better in my brain. Okay. But yeah, this is the set. It's just basically anything that is associated with x, right? If in your relation y is associated with x, then y goes in the set. Okay, now what we are going to do is show that this is true, right? And to do this, we show that they're both subsets of each other. Okay, so let's do this. Now let's suppose y is in the equivalence class of X modulo R. And then we know that X R Y is true. So Y is in the range of R. And or rather, then x comma y is in R restricted to just the set containing x. Why? Because x is in the domain, and also x is in the set containing x, clearly. Okay, and then thus y is in the range of this relation, R restricted to the set containing x. So y must be in R image under x. The set containing x, sorry. Okay. And thus, what was it? The equivalence class of X modulo R is a subset of R image under the set containing x. There we go. Okay, and now we're going to do it backwards. To do that, let's suppose that y is in R, the image of R under the set containing x, right? And y is in the range of R restricted to the set containing x by definition. So, there exists some x in the set containing x such that x comma y is in R. And thus x r y is true. So y must be in the set of y such that x r y, which is equal to the equivalence class of x modulo R. And therefore the image of R under the set containing x must be a subset of the equivalence class of x modulo R. And there we go. That is both sides of the inclusion, and therefore we have proved that the equivalence class of X modulo R is equal to the image of X under the set the image of R under the set containing X. And there you have it. I hope this was helpful, and I will see you in the next video. Bye-bye.